everyone, it's Dr. Drochnik coming to you to tell you a little bit about Lewis structures. Whether this is your first time viewing this video and have never heard anything about what a Lewis structure is or how to do one, to you're using this video for review, you're in the right place. So Lewis structures are going to be models for chemists to see where covalent bonding is occurring. They also show you where the electrons are supposed to be in your Lewis structure as well. So in the steps, I'll go into it a little bit further, but a bond is going to have shared electrons in it, and the ones that are not in a bond, or the electrons that are not being used in the bond, are also depicted in a Lewis structure. And so they're very useful in that they show us what the shape of our molecules are going to look like. We call them geometries, and we'll get to those in a different video. And Lewis structures also help us when we start thinking about how things react and how we want to make different chemicals, when you get into a more advanced class. On your screen now are the 6 steps for Lewis structures that I referred to before. We will be going over each one of these 6 steps, both verbally and as we go through an example in more detail. This is a point in time where I would suggest pausing the video in order to take your own notes on these, get them down in a notebook, and then that way you can use them a little bit later. If you follow these steps step by step, you should be able to get most of your Lewis structures, if not all of them, correct. So let's go on. Number 1, calculate the total amount of valence electrons. Number 2, orient the atoms. Number 3, place a single bond between each atom to connect them. Number 4, place electrons on the outermost atoms one at a time until octet is reached or until you run out of electrons. Number 5, if any electrons are left, place them on the center atom. Number 6, use formal charge and the octet rule to form double and or triple bonds if needed. Let's go ahead and work through the 6 steps using 2 different examples. We'll start with the easier of the 2 first. Before we start with step 1, calculating the total amount of valence electrons, we have to know how many valence electrons each type of element would have. To be able to do this, we need to take a look at the periodic table. And although we cannot see the whole entire periodic table on the screen, what we do need to know is the highlighted colors at the top. Each highlighted color is going to be of importance because it's going to tell us how many valence electrons each element within that column has. So for instance, everything that is in this group 1, hydrogen, lithium, etc., all the way down, every single one of those elements has 1 valence electron. The same thing goes for everything that is in group 2, right here. And when we skip over to 13 through 18, the only thing that is different for those columns or those groups would be the one that's in front, hence 13, cross out the 1, 13 would then be 3. Everything in group 13 would have 3 valence electrons. 14 would be 4 valence electrons, etc., etc., etc. So using this, we can go ahead and calculate the total amount of valence electrons something has. Let's go ahead and start out with CH4. In order to calculate the total amount of valence electrons for the formula CH4, we have to break the formula down into its elements, C, or carbon, and H for hydrogen. We also needed to know how many of each we have. Here you can see that carbon we have 1 of, and hydrogen we have 4 of. We then need to multiply this by the amount of valence electrons, which we just went over from the periodic table. Here you can see the multiplication set up. Carbon is in group 14, cross out the 1, and then that's where the 4 comes from, so 4 valence electrons for carbon. And hydrogen's in group 1, therefore there is 1 valence electron for each hydrogen that is there. We're going to go ahead and multiply those across and add them together, and this step is over. As you can see here, once we do the math, 4 plus 4 is 8, so we have 8 total valence electrons. Let's go ahead and move on to step 2, orient the atoms. In order to go ahead and do this, we have to look at the electronegativity values of all the elements that are within our formula. On your screen now is an electronegativity value chart that I use in my class. The higher the number, the more electronegative an atom would be. So when doing a Lewis structure, you have to find all the atoms that are within the formula and determine which one has the lowest number. The one that has the lowest electronegativity would be the center atom, if a center atom is needed. With this being said, hydrogen can never be the central atom. Now that we have looked at the electronegativity value chart, let's go ahead and proceed with our example. Again, we have to break apart our formula into the elements and look at each electronegativity value separately. As you can see already, carbon has an electronegativity value of 2.5 and hydrogen has an electronegativity value of 2.1. We need to put the lowest one in the middle, with the exception that hydrogen can never be the center atom, as you can see by the note that is on your screen. To be able to orient the atoms, now we just have to arrange all 4 hydrogens around the carbon. At this point, we went ahead and oriented all of the 4 hydrogens around the central carbon atom. You want your hydrogens to be spaced out as equally as possible, hence why one is on top, on the bottom, and to your left and right. For step number 3, we have to place a single bond between each atom to connect them all together. We're also going to start some very simple math out at the same time. So let's go ahead. Here you can see there's a single bond connecting every H to the center carbon. In order to start the math, although simple, there are a few things that we need to know. The first of which is how many electrons are being used in a single, double, and triple bond. At this step, we're really only concerned about a single bond. In a single covalent bond, 2 electrons are being shared. I went ahead and show here the double and triple bond and how many electrons they also use, which a double uses 4 and a triple uses 6. At the bottom though, a really easy way to remember how many electrons are being used is that every line uses 2 electrons. Hence, if you have 2 lines, just multiply that by 2. To start the math that we need to do for our example, we have to go ahead and revert back to step 1 and look at the total amount of valence electrons we calculated there, which is 8. Here we have our 8 valence electrons written down, and we are going to continually subtract how many electrons we use as we go through each step. Currently, we have now used 4 single bonds. Each single bond uses up 2 electrons, so we just used 8 total valence electrons here. Going ahead and showing the math is a good idea. As you can now see, I went ahead and subtracted 8 electrons from the total of 8 valence electrons that we already had, because each single bond has 2 valence electrons, which results in a difference of 0 electrons left over. For step number 4, placing electrons on the outermost atoms one at a time until octet is reached or until you run out of electrons. Using our example from before, we have no more electrons left. Because of this, we do not get to add any more electrons to our structure. Therefore, we just get to skip step 4. Step 5, if any electrons are left, place them on the center atom. Again, looking at our example that we have been working on, we still have no electrons. Therefore, we can skip step 5. For step 6, we do need to look through the formal charge and the octet rule of our structure just to confirm we actually have what we want. So, as the step says, we're going to use formal charge and the octet rule to form double and or triple bonds if needed. Let's go ahead and talk about what the octet rule is and how to calculate formal charge. Here is how I remember the octet rule. Making it super simple, it's the rule of 8. atoms want 8 valence electrons, with the exception, of course there's always an exception in chemistry, that hydrogen only wants 2 valence electrons at most. When you're working through your Lewis structures, this is really what you need to hold on to. Depending on your instructor could give you some other exceptions to the octet rule, but we'll leave that up to them. Now on your screen you can see formal charge and how you go about calculating it. For each atom that is in your formula, you're going to go through this equation. Here you have atoms' valence electrons from the group number. This is the amount of valence electrons from the periodic table that we described in step 1. From there, you want to subtract the amount of bonds that said atom has, 1 for each line. And then at the end you also want to subtract the amount of electrons each of those atoms have. So let's go ahead and work through our structure to see how we go ahead and balance formal charge with the octet rule. Here is our CH4 molecule that we've been working on. Let's go ahead and see if we're done. Carbon is an element that wants to follow the octet rule and wants to have 8 electrons at most. Then we also have the exception, which is hydrogen, and hydrogen only wants 2 valence electrons at most. So let's go ahead and work through that first. Carbon has 4 different bonds that are connected to it. As we already know, each one of those lines contains 2 electrons. So when we count those up, we want to count it as if carbon has all of them. So it has 2, 4, 6, 8 electrons being shared. Therefore, carbon is happy with the octet. Let's go ahead and look at one of our hydrogens. The left hydrogen has 1 bond to it. Again, each bond has 2 electrons being shared. So when we're looking at the octet of hydrogen, hydrogen is also happy because it has the 2 electrons that it wants. Going around the circle of what our Lewis structure is, hydrogen, hydrogen, and hydrogen, each one of those has only 1 bond, so we can say that they're good too. In order to calculate formal charge, let's go ahead and go through that. I'm going to go ahead and abbreviate formal charge as FC. We want to go ahead and calculate the formal charge of carbon, and we want to do the formal charge of hydrogen. On your screen now you can see the work written out. Carbon is in group 14, so it has 4 valence electrons at once. It has 4 bonds to it, so we subtract 1 for each one of those 4 bonds. And carbon has no electrons that are not within a bond, so 0 essentially. If we go ahead and do the math, 4 minus 4 minus 0 is 0. So carbon has no charge here. Let's go ahead and do the formal charge of hydrogen. I think it's safe to say that all 4 hydrogens are exactly the same. They're just located in different positions around the carbon. You can now see the math for the formal charge of hydrogen on your screen. Hydrogen is in group 1, so therefore we write 1 down. We subtract 1 because each hydrogen only has 1 bond to it. And again, the hydrogens don't have any additional electrons, and they never should. If we go ahead and do our math, this also equals 0, so it has no charge. One thing that we have to remember as we go through other Lewis structures is octet rule is going to trump formal charge. However, with this being said, we are going to have some exceptions here and there. So in another example that we'll do soon, the formal charge will exist as something other than 0. But what we need to be paying attention to is the octet rule followed? Let's go ahead and try something a little bit more challenging, and it will also show you how to work through some of the steps that we were able to skip over. At this point, our Lewis structure for CH4 is correct, minus the check marks, of course.